logic in solving it. How do you put various things together? What are the kind of results that you expect at the end? Now, today I'm going to generalize that setting to a much wider class of problems, and that class is known as Hamiltonian simulation. What is the idea? The idea is to understand the dynamics of a quantum system. You start with some initial state, it has some interaction and it reaches some final state, and you want to understand how it reached the final state and then what are the properties of the final state. So this is a very broad class of problems, and we don't have to necessarily break up the Hamiltonian into kinetic energy and potential energy like I did in the case of spatial search problem. It can be much more general situation. The interaction doesn't have to be like a delta function. In case of a spatial search, it can be a more general connectivity between different components of the system, and we try to understand what happens. And the reason for it is twofold. One of them is this understand behavior of a quantum system. This is how the whole science of quantum theory started. You had lots of experimental observation, and then you try to figure out what is the dynamics that will produce those observations. And we have solved it to a certain extent, but still there are lots of open problems in the sense that I give you some material and give you some rules, tell you how it will going to behave in some function of time. You don't really know it for complicated materials. Very simple system, yes, you have some analytical solutions and you can do it, but you go to a more complicated system, we don't have generic prescription which will predict the results. Okay, so this is a part which is kind of science, and there is a complementary part which is technology, and that is design quantum systems with specific properties that you think are interesting. You want to make a new material, you want to make a new molecule, you want to find applications in chemistry or make a new drug or make some new what I call catalysts or enzymes or things of that sort. You don't have a method to do it. So we want to understand that suppose you are given some rules, will it produce this desired effect? That is a technological game in lots of different fields. And how does the simulation help in such scenarios? That yes, you can do a real system monitoring in the sense that you have a quantum system, you just observe it and see how it progresses through various stages, and that will give you some idea of the dynamics. What the simulation part will bring in, it will bring in tunable parameters. That in a real system, you will have to work with whatever the interactions are there, that particular material, and you just simulate it and see how it behaves. But now I can do more with tunable parameters that I will change a little bit and figure out how the dynamics will get affected. And that capability of tuning the parameters to design a variety of different phenomena is very important in all technological challenges, and that is what the simulations allow us to do. That there are tunable parameters which are more general than a system which you will find in some natural phenomena. And to be able to develop new things and new designs, you want to first figure out, if I change the parameter, does it go in the right direction? Might go in the wrong direction, etc. But that is the job of simulation. So everything, all high technology stuff these days, first it is simulated, and then once you are happy that yes, some properties are in the right ballpark, then you go for actual fabrication. So this is the advantage of simulations, and what it should be able to do. Okay, that we want to maintain all those properties, but also the simulator needs to be efficient. There are criteria that yes, you are adding all these tunable parameters, but then it should remain as good as the real system as you can manage. It may not be perfect, but you want to get the control in such a algorithm so that the simulation should remain efficient, and we have to prescribe what are the criteria for efficiency in a generic scenario. Of course, we'll have to put some restrictions. It cannot be just any arbitrary thing, and we are looking for features where quantum mechanics genuinely plays a role. Okay. If all these things which are there in the Hamiltonian, it is just a classical behavior, we are not going to put it on a quantum computer, we'll just work with a classical computer. No big problem inside there. And what is the characteristic phenomena which appears in the quantum Hamiltonian, that the Hamiltonian has not only, at least two non-commuting parts. Because everything is going to commute with everything, we will have classical physics. There is no quantum physics at all. So a quantum Hamiltonian will have at least two. There can be many more components which don't commute with each other. In the kind of spatial search problem, you can say the kinetic energy and potential energy, they are two operators, they don't commute. But it can be much more general than that. But the fact is, the Hamiltonian will have at least two non-commuting parts, and this is basically what makes a problem interesting. Okay. So now let me try to define the problem little more explicitly. So what we have are actually three components in this particular game. One is a initial state, which I will just call psi 0. You have to specify it, where are you going to start from. In a real material, whatever system you work with, you may have some ground state, some equilibrium state, whatever it is, which is easy to start with. You need to be able to specify that. Then there is a evolution, which can be generically specified as a unitary operator, which is exponential of Hamiltonian. The Hamiltonian can be time dependent. There is no necessity that it is a constant. And when it is time dependent, you have to order the evolution from some t equal to 0 by taking individual steps, because when it is time dependent, this kind of feature will appear that h at one time may not commute with h at another time. Then this needs an ordering, which is a standard prescription, and then you have this some final state, and then there is a measurement, which is the expectation value of some operator in the final state. So this is going to be probabilistic in general, and so you have to figure out what is the best way to measure it. Okay. This part is deterministic, that if you are given a precise Hamiltonian, the evolution from here to here will be unique, and it is also reversible because it's a unitary operator. And what will generically happen is yes, okay, let me call this operator some u of t, this whole thing. Now you are going to simulate it, which will incorporate some approximation, and more specifically a discretization, which has to be done on a digital machine. So in practice, what you produce here is a and then you will not get exactly this ut, you will get some approximation to it, and we need, in some sense, the difference between the exact one and the approximation to be bounded. Now, what all kind of things will go into this approximation will have to work out, but the difference has to be bounded, otherwise the whole thing doesn't make sense. And so now the algorithm will depend on all these things which have been put inside it. What is the Hamiltonian? How long is the evolution? How much is the error? Those all will be parameters which you have to specify to get a good result. Some norm, you can take a matrix norm. These are both are unitary matrices. So matrix norm is just if any matrix is there, M, then trace of M dagger M can be a good norm. That's okay. Okay. So now I can state various features which are present in physical systems. And they are generic in the sense that mathematically lots of possibilities are allowed, but in practice, well, your choices are kind of commonly put into certain categories. So one fact is that the system has many components. It may be a complicated system, but you have some way to figure out that there are many parts. Of course, these parts will interact with each other in some way, but you have a kind of labeling scheme that, yeah, I can address these various parts as different entities which will interact according to some rules. Okay. And in our quantum language, you can say that n qubits will generate 2 raised to n, which I'm going to call capital N dimensional Hilbert space. Okay. This capital N will be the dimension of the Hamiltonian or the unitary matrix. So that's what it's going to act. So this for H or U. This is quite generic. It is available often. What is the second common feature? That is, these components have only local interactions. This is kind of guaranteed by the principle of relativity, but it is very general even when you don't have to bring in relativity explicitly. We know that the interactions, whatever they are, they fall off with the distance in almost every material and system that we talk about. And so that fall off of the interaction is absorbed in this label local, and if there is some tail of the interaction left, then we can probably truncate it off and make the things local. If there is a truncation, you have to worry about again what happens over here. But many times it can be justified. So, or just well, kept in the back of the mind that yeah, if I include the range to be expand it some way, maybe I have to include some more corrections to it. But it is quite common that the interactions follow with distance. And yet another properties which, okay, so and that is again, I can give an example of this type. So, e.g., this n components have order d times n interactions where this d is in some sense kind of thing which I was using the last lectures with a number of neighbors. Okay, we have some components, they have some neighbors, they will interact with them, doesn't go very far. This, whatever it is, local means that this number is finite. If n goes to infinity, this number is not going to go to infinity. That's what it is. And last thing which is common is that whatever the Hamiltonian is, we are able to write it down on a piece of paper. Okay, that's our, otherwise we can't even define the problem. What does it mean? That the Hamiltonian, even when this becomes very large, the description of the Hamiltonian is not going to become very large. There can be many ways in which it can happen. For example, there can be a translational symmetry in the system, so that yes, you define it here and it's going to be the same everywhere. So you put many components, no, I don't have to rewrite the Hamiltonian all over again. So Hamiltonian is described by finite number of efficiently computable functions. They are the characterization of all these interactions, but you know the functional form. The function can depend, it can have an argument. For example, it can depend on the location, that the value of the Hamiltonian at one point is different from that at the other point, but then the difference is coming solely from the label of the location. So I can say it is some function f of r. Function is well defined, r can be variable. R can depend on the label of the component. Or if it is a interaction with a variable dependence on the distance, well, there will be some v of r. R can vary from place to place, but the function is itself well defined. So, okay, so But the function, whatever it is, it's something which you can compute, whether it's a polynomial, it's an exponential, whatever it is, it's a gradient, all kind of things can be put inside there, but they are all efficiently computable with some algebraic method. You assume that. And this structure is common, and it kind of guarantees one particular property that in the computer science is labeled as a Kolmogorov complexity. Its a description is that the computational resources needed to describe a system or define a problem, they essentially correspond to the same thing, is the I can be little more general, so it can be quantified because it's a complexity. In terms of the compactness of the description. So the problem can be specified very easily. It has small complex Kolmogorov complexity. If the description is very elaborate, then the complexity is large. And what we are indirectly assuming over here is the complexity of defining the problem is simple enough so that the algorithm will not depend on the description of the problem. You can have a problem which is so complicated that the algorithm and the description become kind of the same thing. We are not going into that territory. You have a simple enough description of the problem, and the algorithm will be kind of independent of that. And that is kind of guaranteed by this sort of generic features. Keep that in mind. So now we can specify some details about what all things are going to happen and what will be the criterion for the simulation algorithm. Yeah. Yes. We can have Hamiltonian time dependent. You'll have to adjust your algorithm to deal with that. One of the parts in which it appears is make this evolution a path ordered product. Okay, so now we can ask this question in this particular setting. Okay. So first the initial state. It's going to live in this n-dimensional Hilbert space. It has n components, capital N components. And if that n component are just going to be some arbitrary set of numbers, there is nothing much you can do about it. You can't reduce the description. It will remain n different, capital N different values. And then it will not really correspond to a compact description. So those kind of problems we generally don't deal with, but you can say if the n components are just arbitrary numbers, what can the quantum description help? And that is the kind of worst case scenario. This state is you can get a quadratic speed up, but nothing better than that. And how can this be understood? So take well, the state or the desired state is the oracle, the target oracle, and then start with some guess with non-zero overlap. That is what the generic Grover's algorithm scenario does. You start with some simple description of some guess state. You want to go towards some complicated function, and as long as there is a non-zero overlap, you can evolve in the two-dimensional plane and it will take you there. And this is the worst case scenario. If arbitrary description is given, there is nothing more that you can do. But in practice, we will have scenarios where the initial state have a simple description. Or for example, in many computer programs, you just start with everything initial register equal to 0. That's a very simple state. Or in many quantum algorithms, you started with an initial state which was a uniform superposition. It could be created much more easily than that. So there are many simple states that can be efficiently created. Efficiently is some polynomial effort in the number of components. For example, the uniform superposition state can be created from everything is equal to 0 by only applying n Hadamard gates. Okay. And is there a generic rule for specifying what are the simple states that can be created in this kind of efficiency? And there is a well-established answer for that. So that I will give without any proof, but in the last semester's lectures, I had pointed out these particular properties. So these states are generated by the subgroup of all the transformations which fell under the label Clifford group. Hadamard operator is included in the Clifford group. So everything which you can generate using Clifford group can be efficiently described in the classical language with this polynomial and effort, and they will generate a wide variety of states, not just very simple ones, but they are created efficiently. A generic description which has more complicated values of the components will go beyond the Clifford group. Okay. So we are going to somehow assume that our problem has this particular property. The initial state, whatever it is, we have a mechanism to generate in some way using Clifford group transformation, which is efficient. Yeah. The final state which we want to reach, it has some description of this capital N components. Target oracle is the language used in Grover's algorithm. Where you want to go. So you want to go to a description which is some vector with some values. That becomes a target oracle. That's why it is an oracle. You have to specify it in some way. If you say that I'm going to start from this initial state, you have to have some description. Description may be too complicated, but you have to have a description. Yeah, so it is given. It's given as a input, and then you can treat it as an oracle.
Is the converse statement also true that any state created by using the gates in Clifford group is like invented converse statement?
Yeah, it can. All states in a Clifford group can be efficiently generated with classical reversible logic. Okay. So that is as much as can be said about this initial state. There is not too much about it. Now we can ask about evolution. What are the criteria or the parameters which are involved in the description for that? So one thing which is that it's reversible. So it should treat both input and output on the same footing. You can go this way, you can go that way. And this problem is a function evaluation problem. It's different than the decision problems which define the class NP. The property of this NP was that, yes, it is a complicated job to find the answer, but if you have the answer, you can verify it very easily. In this function evaluation problem, there is no scope of verification. You started with some initial state and you obtained the final state. Is it right or wrong? You can't tell. And that is why you have to put all this criterion of making it bounded within something so that you have a certain confidence in whatever you got. But it is not this decision problems which typically define this class NP. It's a different kind of problem. And then you have to ask, now what are the parameters that can quantify it? So this efficiency efficient algorithms are, now you can go back to the generic description about what we did in complexity. There was an input which in essence is defined by the number of components, and you want the algorithm to be polynomial in that, okay, not in this exponentially large space. Because the whole structure is reversible, it should be polynomial in the log of the precision. Okay, log of the precision is the number of bits required to specify some epsilon. So epsilon is 10 raised to minus 3. I need 3 decimal digits to specify it, and that is analog of how many input bits are there, how many output bits are there, which specify your algorithm. So it is not epsilon, but it is log of epsilon, the way the properties are defined. And then the third parameters, which is kind of implicitly, it's there, is the connectivity, number of neighbors. Yeah, 1 by epsilon. If you want to make a number positive, that is fine. So this is what we are aiming for. Okay, if you can't get that, then the algorithm is not going to be efficient. It can remain some exponential result, but that is not going to give you something which is interesting from the point of view of simulation. And the comparison with direct physical system, so this is on the simulator. So natural system, I just defined it. It has the complexity and components and T time in which it will do this particular job. And that is a real hardware. This is just what you call mimicry, that simulation is trying to do almost something as almost as good as what a natural system does. Natural system will do the job with n components and t time. You want the simulation to go as close to this behavior as possible. Yeah.
Initial state with capital N components, and when we don't know the target state and given a target oracle, how do you know the number of steps that we require to reach the target?
That depends on the oracle. No, not the oracle, the overlap. Some initial state and the target, the Grover's algorithm, the controlling parameter is the dot product of the two. You have some description of the target state that it will allow you to estimate what that number is. Of course, it will depend on the magnitude of that number, but that I'm not specifying inside this. This is a behavior. If you want to be more correct, it will be 1 over the overlap, whatever will come out as a computational object. In Grover's algorithm, this target size was a delta function, and the initial guess was a uniform superposition. The overlap was 1 over root n. But it can be a different number in more general. I'm just writing it qualitatively, but this number is large, whatever it is. So, okay. So this now kind of gives the constraints of what you are aiming for, and you want to design algorithms with these specific properties. So now I need to fill in various connections which arise because of the discretization of the description. So the discretization can be done using a graph where the components will become vertices and interactions will become edges. and this locality will become that the graph has a finite degree, how many neighbors you have. And then you can look at various kind of scenarios. Some systems are actually easy to describe. For example, the graph can be just like a crystal. There are various atoms and some neighbor interaction, and you want to study that material. Well, it will directly map into the graph in a very trivial fashion, but then things don't have to be crystal. It can be a liquid where everything is moving around randomly. You still have locations and you still have distances, but it's all dynamical stuff and doesn't have regular patterns. And the description, well, it will change. So what can you say about the graph property in general, that if you have graphs with a finite degree, they can be decomposed into subsets which are non-overlapping. Okay. So and this subset in the language of graph theory are referred to as colors. The property of non-overlapping subsets is that the subsets become block matrices that can be easily manipulated in whatever way you want. In particular, here in Hamiltonian situation, you need to exponentiate them, because this is the unitary operator that you want to construct. Block matrices of finite size can be exponentiated very easily. And this strategy of decomposing it into various colors, there is actually a theorem which goes after Weising, and that says that how many of these colors or how many subsets you will need, and this is the answer at the most d plus 1. But if I give you a graph and if I give you a value of d, then find out this decomposition into these colors, that problem is NP complete. Okay. So, well, the theorem can be proved, but it doesn't give you the solution. Fortunately, there are a whole lot of graphs where you can do this decomposition very easily. And in practice, we juggle around with problems, so it falls into one of those categories. Okay, so one of the examples is something called a bipartite graph. Which means that neighbors of a particular point belong to the second subset, and the neighbors of points in the second subset belong to the point in the first subset. It just divides into two parts, and they need only d colors, not d plus 1, and this decomposition is kind of efficient. A common example of a bipartite graph is a set of vertices which can be labeled as even and odd. So every point in the even subset, all the neighbors are in the odd one, and every one in the odd subset, all the neighbors are in the even one. And well, you can write down some symbols. Geometry like a square. So if I call this point even and this point odd, you can see that it's a bipartite graph. And how do this D colors then act? Well, you just have to take all the individual neighbors. So suppose this one is one color, then the same for all the directions in the same subset will be assigned the same color. If I assign some other color over here, I assign some other color over here, and then if I go around with fixing all the D directions for all the neighbors, you can see that these different colors will not overlap with each other. Overlap here means that they meet at the common vertex point. That never happens. And that, now if you try to write down as a matrix structure, it will create a block diagram. There is no overlap between different blocks. So different colors. And the property of the block matrix is that this is like a diagonal matrix. You can calculate whatever function you want with it, and all the different blocks mutually commute in that particular sense. And then what is that analog of the generic thing which I mentioned, that the Hamiltonian has actually at least two non-commuting parts, that means there will be at least two colors. If it was just one color, the whole problem is classical. At least there are going to be two colors in a problem, and then you can have more, like up to D colors in this bipartite graph, and you can figure out how to work with that. So this is one feature of discretization which is going to happen, and we are going to use it. It comes in a different structures, and what I did in the special search problem is I decomposed of the Laplacian in what was called odd and even subset. It's a special case of this particular strategy, where I defined Laplacian as broken up into two matrices. They had different structure, they didn't commute with each other, but individual one I could tackle easily, and then I can define a walk. I think that was used in the flip-flop walk. Yeah. One of the flip-flop or the other depreciation was this staggered scenario, and they all are special cases of this generic structure. We break it up into two parts, and it kind of gave you a good decomposition to work with. Okay. So this is what one aspect of discretization that will enter into the graph, and then we now need to figure out an algorithm which exploits that particular structure. Yeah. They are not vertices, they are actually interactions. Because decomposition is of the edges, and none of the two edges will have a common vertex. That is why it will be some element, if you want to define it in terms of the matrix, but the edges will correspond to an element with index ij, I for one vertex, j for another, and it will be an off-diagonal element. If only diagonal elements were there, there is nothing complicated to deal with. The off-diagonal elements is which require some effort of simulation, and this is decomposing these off-diagonal elements in a particular subset. So, yeah, these are diagonal, and these things are off-diagonal. So that is one part which will go into the discretization. Let me say something about this business of epsilon, or more particularly what you need to do for a function evaluation. I wrote evolution, it is evaluation. How do you bring in this epsilon, and what are the conditions required to make this error small in a certain sense. Okay. And this is something which I had mentioned earlier while defining the so-called bounded probabilistic polynomial class of problems, where I put in a number like 1/3. The epsilon has to be less than 1/3. Now I can give an explicit calculation which justifies that particular boundary. It's not going to be 1/3, it's any number bigger than half, but it can be done. So this is another parameter, but calculation is straightforward. So all that you can do in this function evaluation problem is you will evaluate the function and then measure some property of the final result, which is something I just erased. Some operator is measured, and that operator we need to have discrete values. If it is going to be a continuous description, every time you will get something and you don't know which one is right and which one is wrong. Okay. So we have not specified what observable we are going to measure at the end, but granted that it will be a discrete observable, it is common in quantum theory that some eigenvalue will come out whenever you are going to measure the final state. And the eigenvalue spectrum, we take it is some discrete values. For the qubit, it is just +1, -1, nothing more complicated. So what is the advantage of a discrete variable? That I will get a set of answers and then I can count which answer coming with which particular frequency. I could not have done it with continuous observable. And given that counting, now I can definitely say that this is the most frequent answer, and then I tell that that is the correct result. So for a qubit, you can basically just take a majority rule of binary result. Because there are only two possibilities, I can just say this one is larger and I assign that it's the correct value. And there is not much else you can do even in a more general situation. The advantage is that discrete variable is absolutely necessary, otherwise I could not have figured out what is the correct final state. You can only put a bound. And many times if the value is continuous, you can still do a discretization by assigning it intervals. That this interval I will give it one label, that interval I will give it another label, third interval I will give it another label, and then I will count the frequency within every interval. And that will tell me that this interval is more frequent and the answer is somewhere inside there. But you have to do that discretization in some sense or the other. So now I will just take the binary case because the answer is easy to obtain, and let me just say that let epsilon be the probability of wrong answer, and then when epsilon is less than half, it can be arbitrarily suppressed with extra you have to work a little harder, extra effort, but extra effort will be polynomial in this log 1 over epsilon, something which I wrote down over here, which is acceptable. But with this effort, I can suppress the probability to large number, and now let us do some counting. So let there be R such trials, which in this language is this number of independent evolutions. So whatever algorithm I construct, I run it capital R number of times, and I measure some observable at the end. So it will be an overhead. Overhead of the complexity will be the factor of R. I have to repeat the algorithm so many times. And now I can write down rather trivial identity which describes what is going to happen in this R, and that is just a simple identity which is a combination of the failure probability and the success probability. What power of R, I don't know, but it doesn't matter. And then I can perform a binomial expansion, which starts with says 1 minus epsilon raised to the largest power plus this binomial coefficient going all the way till the last binomial coefficient will again be 1. And now you can ask what happens when I apply the majority rule on the selection, that I will get some boundary which will be defined by how many times is 1 minus epsilon, how many times there is epsilon. And whichever number is larger is the winning answer. So here correct result, and there is a wrong result, and the boundary because of the majority rule is R by 2 and this part is larger, this part is smaller, so I have to truncate it. It is the smaller integer. Let me put some values where this half is giving a fraction. So suppose I have 3 trials, and then the failure will arise when at least 2 trials are wrong. And that means that there will be some terms over here, 0 wrong, 1 wrong, no problem. But 2 wrong and 3 wrong will have a problem. And what is the number for 2 wrong or 3 wrong? I have to write it in terms of 3 by 2. And yeah, it will be the larger of the integers where the boundary will come, that this number dividing line is at 2. A 3 by 2 has to be rounded off to 2, little larger integer. But anyway, this is not a major problem, it's just being a little bit mathematically rigorous. So now I ask, what is the total frequency or the total bound? So the probability of wrong result, it can be bounded. I'm going to take all the terms over here, they will have different power of epsilon, but I'm just going to take the what you call the leading term, and all the subsequent terms are decreasing. Okay, so this is epsilon to the power r by 2. The following term going all the way to epsilon to r are all going to be smaller than that. That is a bound I can produce, and then all the sum of the whole terms is the sum of the binomial coefficients, which are all going to be there. I just simplified my work by factoring out this power epsilon, that I can sum the binomial coefficients very easily. And I know the answer of the sum of the binomial coefficient, because sum of all the binomial coefficients from here to there is 2 to the power r. Cutting it half the way through, that is going to be 2 to the power r minus 1. And well, then there is a power of this 1 minus epsilon, which I can also include, but for the time being, yeah, it's something that can be ignored, because whatever it is, 1 minus epsilon is less than 1, and I'm just putting an upper bound. It doesn't matter. And so this number is 2 raised to r minus 1 times epsilon r by 2, and this can be made arbitrarily small provided this factor wins over this. Both have r in the exponent in some particular manner, but you want this one to win, so it goes to 0. And that means epsilon has to be less than half. So with epsilon less than half, this probability goes to 0, or not 0, but it can be made small. And what you need is a r of the order of log over epsilon. What is the actual value of r will depend on how small the probability you want to make. But this is a generic prescription that yes, you start with a number which is less than half, you can push it down, and the extra effort, the repetitions required, depends on what values of r you started with it. And this half is definitely related to the prescription, which is the majority rule. You have to be on one side and not on the other side. And this is what went into defining the BPP problem, that you wanted a success rate, but the success rate had to be some value greater than half. I took the number 2/3 because many theorems they just write 2/3, nothing specific about 2/3. Any number larger than half is okay. But this is something which you have to do to get this error under control, and that is r is basically the overhead. When you construct an algorithm, it will be part of the complexity, but since it is log of 1 over epsilon, it is within this particular condition which we can manage. Okay. So this is one caveat. Then there is another consequence of discretization, which is the variables will be represented as some digits. It's a truncated description. Essentially, the real number is converted to an integer. So there is a round of error. And you have to ask, well, what is the size of that round of error? How it is going to accumulate. So that can also be given the quantification, which is not too complicated. So we have to evaluate is but fortunately our number system is such that some number of digits are to give some label. So let me call it B. Digits precision from delta is 2 to the power minus B using a binary label. So let me call it bits. And this delta is going to affect the final result, and ultimately it will become part of the epsilon, a different contribution to the epsilon, not from the algorithm, but just for the discretized definition. So what is a Hij? It is some function which is given to us in some simplified version, and you can write it as, well, some well-known mathematical function, or even just as a approximated polynomial. So that is also a fact that finite precision functions have efficient for example, you have sine or exponential or log or 1 over r or any of those kind of behaviors. But one thing which we already took into account, that we made everything local. So none of the ranges are going to go out of bounds. So we want a good approximation to the function within that particular range. And then you can have what you call a fit to the function by something which you can calculate easily. And what is known generically in mathematical fitting theory, that a function on a finite interval you can fit to high precision just by a polynomial. You can find such polynomial. Of course, the degree of the polynomial will depend on how closely you want to fit the function, etc. But they all have polynomial description. The degree in some sense is decided by the number of bits which you have in the value. Because after some point it's kind of redundant in the sense that it is discretized and the neighboring values cannot be put in the same polynomial anymore. Okay, so you have to have one neighboring point in one polynomial, another neighboring point in another polynomial, things like that. The degree is basically dictated by the amount of precision which you need, and then this can be evaluated with order B cube effort. This is a simple counting. B is for sum, B square is a multiplication, and B cube is a polynomial just evaluated by the simple arithmetic procedure which we learned in school. So sum and multiplication easier, then you have various different powers and you add them up together. The point is, if you have a function defined on B bits, any function can be evaluated with order B cube effort. and then the total error is just going to be order b cube, or rather it's bounded. So times numbers of uses in whatever the algorithm. So this uses will again be in terms of addition and multiplication, because algorithms don't do anything else, and individual terms has this much error, and then how many times you are going to use it. Well, there is an upper bound that the error cannot be larger than the sum of all the individual errors. This is just a triangle inequality in some particular manner, and that is something which you need to keep in mind. And the fact which now appears over here, that if I say that this is going to be less than epsilon, whatever I constructed, or I have to bring in this delta in there. So total error is actually not order b cube, but it is in the individual step, the error is delta. Sorry, I made a mistake. I evaluated with so much effort, but the final result, the precision is delta. So this I was calling generically epsilon, and this will be the criterion coming from triangle inequality that the error will not be exceeded that. The point is now I can try to invert this relation to how many bits I want. So the number of bits necessary is b, which goes as a log of 1 over delta, and that will go as a log of 1 over epsilon up to some, well, I have to take it the other side, so this is number of uses. Something like this. The important point is that this is a resource requirement in the calculation, how many bits of precision I am going to keep in representing various quantities, and it comes out as log of 1 over epsilon. Again, falling into this particular criterion that yes, it is needed, but yes, it is within control. So these are the kind of things which arise from discretizing the problem, but we need to do that to have a reasonable looking algorithm, and the errors and the overheads are there, but they are kept under control. So yeah, I will stop today here. What remains is actually now the major part of the algorithm. How do I evaluate that unitary operator? I describe various other ingredients, but the unitary operator has to be now constructed. And that I will continue next time.